We're back into section 3.6. This video kind of picks up from where we left off on the last one. We were doing some work with exponential expressions and logarithmic expressions, and we know that because we only have natural logs and common logs on our calculator, if you're given an exponential expression that has a base that's different than either e or 10, it could run into problems as far as the calculations. I know we can always go to the change of base formula that we've talked about before as well, but I'm going to show you quickly and then an example of rewriting base, let's say base b an exponential expression into base e exponential expression. Alright, so right here it says let t and b be real numbers, b is greater than 0, not equal to 1. Then b to the t is equal to e to the natural log of b times t power. Now you can think about that. If I start with e to the natural log of b, which we know is b because of properties of exponentials and logarithms, then what I'm going to do here is I'm going to think of this times t, this expression here, multiplying it, raising it to the t power as this, using the power of a power property of exponents. And of course this right here we know is b, so that's b to the t. So you can see that this expression here is equivalent to this expression. Now again, you're not always going to have to fall back on this, but it does come in handy on certain occasions. And you'll see this also in calculus. So if it says here p of t, this example, given p of t is equal to 10,000 times 2 to the negative 0.4 t power, we're going to rewrite this using base e. Well, that means I'm going to take this expression right here, so I'm going to do a little scratch work here. We'll get this started. P of t is equal to 10,000, and then we'll put the rest here in just a second. Let's look at 2 to the negative 0.4 t power. Now, according to what I just indicated here, using this property right here, that this is equal to e to the natural log of 2, that's your base, times the exponent. Which I'm going to rewrite. I'm going to put this first, it just looks better that way. So now I'm going to replace in my expression here with this, times e to the negative 0.4 t natural log of 2. Now again, you may look at this and you say, gee, it seems like a lot of work. Well, what happens is that when you're working with the natural base and the natural log, then natural base exponential expression, then what happens is a lot of times the work is easier in this form, especially when we get to calculus and we're taking derivatives and or perhaps even integrating something, which again is just down the line a little bit. So this is a good one to remember right here. Put that in the memory banks. Now, one of the types of exponential growth and decay, of course, perhaps the most classic type of problem has to do with half-lives of radioactive materials. And carbon-14 is a great one because it's found in, I think, pretty much every living object of any type. And the half-life of carbon-14 is approximately 5,720 years. Now, with that in mind, the example, use the function q of t equals q sub 0, that would be the initial amount here, of e to the negative 0.000121 t, determine the age of a piece of wood that has 42% of its carbon-14 remaining. Oh, remaining. How did I spell that? Holy moly. Remaining. It would help if I could spell. There we go. And we're going to round to the nearest 10 years. Okay, now, this number here comes through deriving this formula because of the 5720. So you say, well, that seems like it's pulling numbers out of thin air. Okay, so now in this case, we're trying to determine the age of the piece of wood that has only 42% of its carbon-14 remaining. So that means we're trying to solve for t. And this expression, at that time t that we're searching for, it's only 42% of what you started with. And you started with q sub 0. So what I'm going to do is I'm going to write this as 0.42 of q sub 0 is equal to q sub 0 e to the negative 0.000121 t. I'm going to divide both sides by q sub 0. And I'm going to get 0.42 is equal to e to the negative 0.000121 t. Now to solve for t, we've got to get it out of the exponent. Because it's a base e, I'm going to take the natural log of both sides. And then this expression, of course, is equal to the exponent. So I'm going to kind of flip-flop the sides. I'm going to write negative 0.000121 t is equal to the natural log of 0.42. Now I have to divide both sides. I ran out of room, so bring it up here. I have to divide both sides by the number that's multiplied times t. So negative 0.000121 t divided by negative 0.000121 is equal to the natural log of 0.4. And I'm going to have to get a calculator, that's for sure. Negative 0.000121. And I get t is approximately, now we're going to do this to the nearest 10 years. So I have to get a calculator out and I have to do the division here. As it turns out, this is 7,169.426 when I do the division. Now that kind of makes sense because you have less than half what you started with, and that would take 5,720 years, so it should make sense that this number, although written poorly here, let's say we do a little bit better than that. And what was it, 426? Would be more than 5720. And so to the nearest 10 years here, looks like this is going to take, it would take 7,170 years, this would be approximately, for 42% of the original amount of carbon-14. I abbreviated it that way as well. I must have been half asleep when I wrote this problem out. Of carbon-14, it would take 7,170 years for 42% of the original amount of carbon-14 to remain. Okay, so there's our guy right here. Now, exponential growth and decay, there are numerous applications, but half-lives involving radioactive material, you're going to see this not only in this textbook, but as I mentioned before, you're definitely going to see this type of problem in calculus. Speaking of a type of problem in calculus, there's the logistic growth model. Now, the logistic growth model pretty much shows up in a simpler sense in Calc AB, but definitely in Calc BC. And it's just a different kind of growth model for involving an exponential expression, as you can see here in the denominator, e to the opposite of bt. It's kind of a tough one to explain. It's as if you have like, let's say you have a field that's fenced off, walled off, and you have two rabbits that are in there, and there's plenty of food and such, and the two rabbits, well, the population of the rabbits is going to increase quickly. It's going to start out kind of slow, you know, and then as you get more and more rabbits, it's going to pick up, but eventually it's going to level off. And you say, well, why would it level off, you know, rabbits? It's going to level off because they're in an enclosed area, and there's only going to be so much food. And so eventually it's not going to be able to just grow without bound. I mean, it's going to eventually cap off because of the limited amount of food in a fenced off area or walled off area. So that's what the logistic growth model kind of explains. You can see here the rate of change, which is an increasing rate of change, but it's increasing quickly. The increasing is increasing. Now notice the way your curve looks here. It's kind of bowl-shaped upward here. Well, that's referred to as concave up or concave upward. It's when your rate of change of whether it's increasing or decreasing is increasing. And then all of a sudden it kind of pauses for a second and then it slows down. So your increasing is decreasing, if that kind of makes sense. The rate of change is decreasing. Now notice that this is kind of an upside down bowl shape, and that's called concave downward. This place where it changes from concave upward to concave downward is called a point of inflection. I wrote it out there. I don't know if you can read it very well. And just another topic that you're going to study in great detail in calculus. Now what we need to do is we need to try a problem or two that models using this logistic growth model here, and that's what we're going to do next in the next video here. So make sure that you look over this and practice this half-life type of problem, because you are definitely going to see him again.